Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to discuss RBF networks, because as you'll see, they can be useful in reinforcement learning. RBF stands for Radial Basis Function. They allow us to proceed to the next step of using function approximation. There are two ways to think of an RBF network. The first way to think of an RBF network is that it's really a linear model where we've done feature extraction first, and the features happen to be RBF kernels. We'll be discussing what an RBF kernel is shortly. The second way to think of an RBF network is that it's a one hidden layer neural network with radial basis functions as the activation function. Keep in mind that when we first talked about neural networks, we actually looked at them from the reverse perspective. We first looked at the neural network as a big nonlinear function approximator, but then we learned that one way to think of the hidden units is that they were automatically learning feature representations of the input. So what is a radial basis function? It's basically just a non-normalized Gaussian bell curve centered at some center point which we'll call C. C is a vector that lives in the same vector space as the input vectors. Notice how the function depends only on the distance between x and C. So it doesn't matter if x is to the left of C or to the right of C, only the distance matters. That's where the term radial comes from. You can see that the maximum value is 1 when x is equal to C. It then approaches 0 as x goes away from C in any direction. One good question is, how do you choose C? Another good question is, how many C's should you choose? So the number of C's we choose is basically the number of hidden units there will be in the hidden layer. Each hidden unit corresponds to a different RBF with a different center. These centers are sometimes called exemplars. There are a few different ways to choose exemplars. In support vector machines, or SVMs, the number of exemplars is equal to the number of training points, and in fact, they are just the training points themselves. This is one of the reasons why SVMs have fallen out of favor. They don't scale to the data sizes that we have today. Because each training sample becomes an exemplar, training an SVM is order O of n squared, and prediction is O of n, where n is the training sample size. This is an important piece of deep learning history, because SVMs were once thought to be superior to neural networks. Another method is just to sample a few points from the state space. This allows us to limit the number of exemplars we use. Remember that env.observationspace.sample allows us to sample from the state space of the environment. At this point, how many exemplars we choose is just like how many hidden units you should choose in a neural network. It's a hyperparameter that must be tuned. Luckily, although we could, we won't write any code to do the RBF kernel transformation, since these capabilities are already in scikit-learn. Also, our implementation would be unnecessarily slow. The scikit-learn implementation is called RBF Sampler, and it implements a Monte Carlo algorithm that allows us to do the computation much faster. As usual, this has a standard scikit-learn interface. We create an instance, call the fit function, and then from that point onward we can call transform. So now that we know what an RBF is and how to do the feature transformation, the rest should be easy. We pass the features into a linear regression model and use gradient descent to update the parameters of the linear regression model. Notice how, unlike a feed-forward neural network, the features don't change as we learn. The exemplars we chose at the beginning will remain the same forever. Although this might seem restrictive, it actually works better than a plain feed-forward neural network where we try to run stochastic backpropagation through the whole network. Okay, so that was the perspective where, instead of using polynomials as the feature extractor, like we did in the last course, we use RBF kernels as the feature and then put a linear model on top. The other perspective is that this is actually a one hidden layer neural network. Remember that a one hidden layer neural network is just a nonlinear transformation at the hidden layer and then a linear model for the final layer. Well, this is exactly what we're doing here. An even closer connection can be made if we recognize that a dot product is actually the cosine distance as well. In both cases, we first calculate some kind of distance between the parameter and the input, and then we apply a nonlinear function on top of that. This gives us the value at one hidden unit. It's an interesting connection, but that's as far as it goes. Now let's go through some practical implementation details. You may have noticed that the RBF kernel has a scale parameter, which is like the variance of a Gaussian. Since we don't actually know what scale is good, or perhaps multiple scales are good, scikit-learn has tools that allow us to use multiple RBF kernels with different scales at the same time. This is called a feature union, and it essentially allows you to use multiple feature transformers of any kind, not just RBFs, and then concatenate the individual feature vectors together to make one big set of feature vectors. We'll also be standardizing the data before applying the RBF kernel. sklearn has a class for this too. It's called standard scaler. Another opportunity to make use of scikit-learn is the linear regression component with gradient descent. Scikit-learn already has a class for this called sgdregressor, so we are going to make use of that as well. Unlike typical scikit-learn models, instead of calling the fit function, we'll be using the partial fit function, which allows us to do one step of gradient descent only, which is what we want. At the same time, sgdregressor behaves a little strangely compared to what you would expect from a linear model. First, if we don't call the partial fit function at least once, then it won't work because it hasn't initialized any parameters. But at the same time, the first thing we need to do is make a prediction from it, because to do Q-learning we need to take the max overall actions. In order to get around this problem, we'll call partial fit with some dummy values, specifically with the start state as input and 0 as the target. The second thing that's weird about sgdregressor is that by setting 0 as the target, this is going to make all the predictions 0 for a while. This is weird because if we were actually using a linear set of weights to make the prediction, then the prediction wouldn't always be 0. However, this quirk is actually useful because for our next task, which is the mountain car environment, at every time step we get a reward of -1. That means a Q prediction of 0 is higher than any return we can get, and hence it allows us to use the optimistic initial values method of exploration, which we looked at in the last reinforcement learning course, instead of epsilon greedy. I'll give you the option of trying both in the code. Here's some code to try if you want to prove this to yourself. Feel free to pause the video so you can try it out. The first step is we import sgdregressor and initialize an instance of it. Then we fit an input vector 0, 0 to the target 0. Next we do a prediction on 0, 0. We get 0 as one might expect. Then we can try some other predictions. You'll see that no matter what input we try, 0, 1, 1, 0, 1, 1, or even 99, 99, it still predicts 0. This clearly wouldn't be the case if we had a static vector of size 2. The next implementation detail we need to discuss is a technique used by deep Q-learning as well. Specifically, instead of trying to model Q of SA with X as the input vector, that is some feature transformation on the state S and action A, we'll instead just make X the transformation of the state S. Since the actions are discrete, we'll instead create a different linear model for each action. So in the case of mountain car where we have 3 actions, left, right, and do nothing, we'll have 3 linear models, all giving us the Q for a separate action. Another way to think about this is that it's a neural network with 3 output nodes. This is exactly the approach we'll be taking when we do deep Q-learning. And lastly, I mentioned earlier that we are going to be looking at the mountain car environment next. If you don't know what mountain car is, you can visit the wiki page and the documentation page. It basically works like a swing. You're in a car trying to get to the top of the mountain, but your car can't generate enough force to go straight up the mountain. You therefore need to swing back and forth to gain enough momentum so that you can be propelled to the top. If you look at the wiki, you'll see that mountain car states only have 2 variables, position and velocity. Unlike cart pole, the velocity cannot be unrealistically large. So that makes this problem a little easier. One of the functions we'll be plotting is called the cost to go function, which is a strange name, but it's just the negative of the value function. This is what they call it in Sutton and Bardo. Because the state space is only two variables, this allows us to plot the cost to go function as a three-dimensional plot, which we'll be doing in the code.